another very good question. What about the endpoints? So, what?
When it is the regular continuous, the average continuous that we used to see, it has arrows.
Arrows where?
At the ends.
Oh, I see. Right. Oh, yeah, that's true. The arrows. Right.
So they imply.
Yeah, they imply that you're talking about a kind of okay. The thing here is that the domain here is a closed interval. Okay, whereas when you're talking about those arrows, the domain is like an open interval. I think I can say that. So here, I think we say the derivative doesn't exist here. And I would say, I forget technically how it works out, but I would say that, remember, like we just said, that the derivative is a limit, right? But it's not like a left-handed limit or a right-handed limit. Remember, we have left-handed limits and right-handed limits. It's the full limit, the full general limit, right? So it has to have the left-handed side has to equal the right-handed side, right? Remember that for limits? Remember that? So this, when we write this, we have to be able to talk about the left-handed and the right-handed side, right? Otherwise, we can't write this. And here, we can't talk about the right-handed limit. Coming in from this side, there is no stuff on this side. So we can't talk about the right-handed limit there. So I think that's the way you would get to the fact that the derivative doesn't exist at this point. But I have to go back and review, see if that's technically the way they would deal with this. Okay, but yeah, obviously this endpoint is a problem. Okay? Okay, but anyway, that's one kind of problem, but this is a kind of more interesting problem a little bit. So right here, the derivative doesn't exist, and right here, the derivative doesn't exist. Okay, now, so as I said, where is the maximum? When x equals 6, right? I think everybody got that right. And where is the minimum? X equals minus 6, okay. However, this is some kind of maximum, or at least it's a point of interest. Okay? And we want to give it some name, and it seems reasonable to call it a kind of a maximum. Okay? It's not the maximum, but still, it's a kind of a maximum. We may as well call it some kind of maximum. Okay? So instead of calling it the maximum, which is over here, we call it a local maximum, or a relative maximum. So local or relative means that if you limit the discussion to just some small interval around here, at least within that interval, it's a maximum, right? So that's called a local maximum. Now, you might say, okay, well, what about here? Why can't this be a local maximum right here? So what's the idea? If you limit it can you find some interval around this point where this is the highest value? No, you can't, right? You can't find an open interval. You can find a closed interval. That's not what the definition is. Can you find an open interval around here for where this gives you the highest value? No, right? So that is not a local or relative maximum. Whereas here, can you find an interval? Yeah, it's not going to be a huge interval. Like if you go to here and here, that doesn't work, right? Then this is the maximum. But you can find some interval, like this one here, where it is a maximum. That's what's the technical definition of local maximum or a relative maximum. Okay, and the same thing for here, right? A relative minimum, right? Or a local minimum. Okay? So we have these terms. It's just like language for us to, that makes our discussion handy. this language is handy for our discussion. Okay, I think I said, was it last week, did I say that Eskimos have like 100 words for snow? Did I say that? I don't know if that's exactly true, but I heard that many years ago.
Yeah, more if you consider different dialects.
Oh, maybe, yeah. But I mean, the idea behind that is, I guess, that, you know, they live in snow, so they distinguish between many kinds of snow, right? For them, it's, you know, it's important, it's useful, right? And here, it's useful for us to develop some language, you know, about these situations, these graphs, these minimums and maximums, and so on. Okay? So, so we have that, all right? Any questions about that? Okay, how about this one? So, where is the absolute maximum for this graph? 0, right? Where is the, are there any, okay, by the way, every absolute, no. This is also a local maximum, right? Because you can draw an open circle around it, an open interval around it, and it's a maximum in there, right? So it's an absolute maximum and a local maximum. I think the book adheres to that terminology. Okay, most books do. Okay, they'll call this not only an absolute maximum, but a local maximum. Okay? Now, where is the absolute minimum? At 4, right? Yeah. And I think we should also call that a relative minimum. Okay? And then these things are not, right? This is neither a maximum nor a minimum, and this is neither a maximum nor a minimum. Okay? Any questions about this? Okay. All right, so we covered that now. Okay, now let's go to how we can do this using, if we don't have a picture. So if we have just a formula, how can we find the relative and absolute maximums and minimums? Altogether, those are all come under the heading, come under one word called the extrema. Okay, how can we find those if we don't have the picture? So suppose we have, let me just construct this. Suppose we have this function. Suppose we have that function here, f. Now, we don't have a picture for that, right? But how can we find the maximums or minimums, right? Usually, you don't have a picture. You just have a formula. And you have to find it. Okay? So we use the idea that when we have it, if the function is continuous, so if it looks like that, for example, we use the idea that the relative maximums will occur. We use the idea of the derivative or the slope, and we said what? That what about the slope there? It's 0. So we say, oh, well, whenever there's a relative maximum or minimum, the slope is 0. So we use that idea. Okay, so we say, okay, well, what we'll do is we'll find the derivative and then find out where it's 0, because that's where the slope is 0. So we find this derivative. I constructed it so this would be nice. So it's what? X squared, right? First term is x squared. Second one is 10x. Third one is 16. Okay, which can be factored into this. X minus 2, x minus 8. Okay? So now we said we want to find out where the slope is 0, where the derivative is 0. So we set it equal to 0. And we see that it's 0 at 2 and 8. Okay, so we know that we have a curve which has is flat here and is flat here. Okay, but we don't know how high it is, where it is. And we also don't know, does it look like here, 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 here. So one pattern is it could look like this, like that. That's possible, right? Another pattern is it could look like here. Oops. Sorry. Oh, I didn't mean to do that. Okay. Here, 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 and here. I'm sorry. Here and here. It could look like this. Right? That's another pattern. And there are a couple other patterns also, right? That are possible. But I don't think there are too many patterns that are possible. I think there's only 4 patterns that are possible. So one thing we could do to find out, like, is this, so if it's the white one, it's not a local maximum here, and it's not a local minimum, right? And here also it's not a local maximum or a local minimum. But here, if it was the yellow pattern, it would be a local minimum here and a local maximum here, and so on. So one thing we could do is just check points to the left and right. So we check 2, we check 8, we check something to the left of 2, something to the right of 2, which we can also use for to the left of 8, and something here. So if we check those points, we can figure it out, whether it's a local minimum or a local maximum. So we'd have to, like, say 1, 2, let's say 5, 8, and 10. Okay, so let's do that. See what happens. So we're going to do x, 1, 2, 5, 8, 10, and what are we doing? We want to check the height. F of x, not the derivative. Right? We're not looking at the derivative here, we want to look at the height, right? At different places. So when x, 1, what do we get? Look, we have to do this. Maybe we don't want to do it actually. What do we get? 1 plus, yuck. 1/3 minus 5 plus 16 plus 5, right? We have to do that. Right? That's when we put in 1, right? When we put in 2, what do we get? 8/3 minus, what am I putting in? 2, so that's 420, right? Plus 32 plus 5, right? Actually, we don't need the 5 there, because we can just drop off the 5 for each one. But anyway, okay, 5. Now what do we have to do? We have to do 125, right? Over 3 minus, what did we do? 125 plus 80 plus 5. Okay, anyway, we have to do all of this, right? and then check. And then we know this is high, this is low, this is high, this is low, and so on, right? Okay? And we can figure out which is the local minimum and which is the local max. We can figure out, is 2 a local minimum? Is it a local maximum? Or is it neither? Right? And we can figure out, is A a local minimum, a local maximum, or neither? Okay? So that's one way to do this. Okay, but there's another way, and that relies on this idea. If you have a curve like that, let's talk about the derivative at different places. Let's say at A, B, C, D, and E. Let's talk about the derivative at those different places. So, yeah. So what about at A? What about at C? What's the derivative at C? What's the slope at C? 0. The derivative is 0 there, right? What's the derivative at A? So obviously you can't give me a number, but I just want to know, is it positive or negative? So is the slope positive or negative? Negative, right? This is the line. Right? That has a negative slope, right? So the derivative is negative there, right? And how about at B? Is the slope is the slope positive or negative? Negative. So the derivative is negative there, right? And what about at D? It's positive. And what about at E? Positive. Okay? So we know that, right? So when the derivative, when it's, and another thing is that we can also say this: if f is decreasing, then okay. So what do I mean by a function is decreasing? So this function is decreasing. Decreasing means as you move from left to right, the y value drops, right? And increasing means as you move from left to right, the y value increases. So this function is decreasing, and this function is increasing, right? Now, this function is decreasing here and increasing here, right? Okay? So if f is decreasing like this, what can you say about the slope? Or what can you say about the derivative? It's negative, right? Then f prime is less than 0. Right? The derivative is negative. Right? And the other one is what? If f is increasing, then what? F prime is what? Greater than 0. Okay, now you should know in logic that when I write if blank, then blank, that is not the same as, let's call this one P. Whatever I put in here, I'll call that P. And I'll call whatever I put in there Q. That's not the same as if Q, then P, right? Those are not the same statements. For example, you can say P is Thomas lives in Beppu. Okay, and Q is Thomas lives in Japan. Okay, so the first statement would say, if Thomas lives in Beppu, then he lives in Japan, right? That's different than saying, if Thomas lives in Japan, then he lives in Beppu, right? Right? One of those is definitely true, and the other one is not true. right? So when you reverse these, that's not the same thing, right? So you might, when you have an if P then Q, suppose you can prove that that's true, that doesn't mean that you proved if Q then P. That's a separate statement, right? So the same thing here. We said if F is decreasing, then F prime is negative. That's not the same statement as if F prime is negative, then F is decreasing. But actually they're both true in this case. So we often write that as if and only if. If and only if. And sometimes in math they write if and only if like this. If, too. That's if and only if. Okay, so in this case it's true. They're both directions are true. Okay? But it doesn't have to be that way, right? Over here it wasn't that case, right? Okay? So anyway, so this is both ways. Okay, and this is both ways. Okay, so going back anyway, what did we say here? If it's decreasing, the derivative is negative. And also, if the derivative is negative, then it's decreasing, right? And here, if the derivative is positive, it's increasing, right? Okay, so how is that going to help us with finding the maximums and minimums? So let's think about it. We just found that our function is flat at 2, and it's flat at 8, right? Now we could go through all of this that we started to do over there and do it that way. But another thing we could do is we could check here, is the derivative positive or negative? We could check here, so this is a point to the left of 2, and we can check a point to the right of 2, is it derivative positive or negative? So if I find out that